Welcome to TalkCast and to part 4 of chapter 9 of The Fabric of Reality by David Deutsch, Quantum Computers. This is episode 193, if you can believe it. And today we finally reached the conclusion of that chapter. It's been a long time in coming, I know. And this one is going to be a little different to all of the others because we're going to be going into quite some mathematical detail, but not too much. Don't worry. There is only a little left to read from the book itself in terms of this chapter, chapter 9. But in a sense, it's the crescendo part of the book about quantum computers. As I've said throughout my discussion of this chapter is worthy of being a book in itself. We will see that again today because here we get to a very practical application of quantum computing. And we get to do a little bit of, as I've just said, mathematics, a little bit of fun mathematics along the way. We're going to outline and spend most of the episode outlining Shor's algorithm and some of the mathematics underpinning Shor's algorithm. Shor's algorithm, discovered by Peter Shor in, I think it was 1994, is one of the most important quantum algorithms that is known. And although it does get a significant mention in the chapter, in the part of the chapter that I'm about to read, right at the end of the chapter, and David provides a great overview of that, I thought it might be useful for some people, it might be interesting for some people to drill down into at least some of the details. Not all of them, though. Throughout my outline of Shor's algorithm, I'm going to provide links to other resources that you might want to go to in order to go even deeper than what I'm about to do now. So this is going to hopefully bridge the gap for those of you who are fans of the work of David Deutsch, in particular The Fabric of Reality, and would like to understand some of those higher-level graduate physics lectures that you sometimes encounter on YouTube when you go looking for the details of quantum theory. People are often asking me, what book should I get in order to begin understanding quantum theory? What text should I study? And I always say to people, well, go to YouTube. And unfortunately, when you do go to YouTube, a lot of it is presented at the graduate level. It already presumes that you've done, sort of a year or two of undergraduate physics, at least, not to mention the mathematics, in order to understand some of this stuff. So what I'm hoping is that with this episode, I bring you to a level where you can then go off to those other YouTube channels that are at the high graduate physics level and at least begin to have an insight into what they're talking about. But you won't need any graduate level physics and you won't need any graduate level mathematics today. Like I say, this is the whole purpose of this is so that you can get to a point where you might want to go and have a look at those professional physics professors that are talking about, for example, Shor's algorithm and the textbooks that explain this stuff as well. Some people say that the beginning of infinity, Fabric of Reality, is already at a higher level. And some people say that TalkCast is sometimes pitched at too high a level. I suppose I can take that as a compliment, or not sometimes. I'm actually aiming, with these episodes and with what I do here, to have a resource which requires as little prerequisite knowledge as possible. And, incidentally, episode 192, which was not squarely about the work of David Deutsch, it certainly, as always, mentions David Deutsch and his work. That episode 192 was an exception to all of this in two respects. It wasn't about the fabric of reality and the beginning of infinity, or even necessarily Popper, but it did assume a fair bit of prerequisite knowledge of TalkCast. I'm assuming if you listen to episode 192, which is all about the sources of ideas, well, at least that's kind of what it's called. What is the origin of our ideas? And spoiler alert, I don't answer that question. I answer a different question. But what I'm doing there is I'm assuming you're a fan of TalkCast and you've listened to lots of other TalkCast episodes and you know where I'm coming from, so to speak. So yeah, I recommend listening to that because, that's one exception to the rule that I normally have, that you can just come to TalkCast without any prerequisite knowledge. And on the other hand, I'm also trying to say some hopefully original things there as well. So that's also a departure from what I normally do. Here in this episode, I'm not going to be saying so much that's original, certainly not original from me. I'm not coming up with any new ideas here. I'm stealing the ideas of others, so to speak, borrowing their content. So there's a difference, Episode 192, assuming a lot of background knowledge, lifting off from the presumption that for example, there are two kinds of knowledge in the world. There's mimetic and there's genetic, and Popperian epistemology just is the way that we explain how knowledge grows and is improved over time. All that kind of stuff is just assumed as prerequisite knowledge. So you're starting at a high level there. But here today in this episode, I'm going very, very basic from the start. Indeed, I'm going to go over some ground that we've already trodden in the previous 3 episodes on quantum computation so that we have fresh in our mind the knowledge required to go even further today. The fundamentals that I'll be talking about today, going as deep as I can on some of these fundamentals, is going to involve, literally things like high school level mathematics. I'm not going to go so deep as to, teach people how to count or speak English or kind of that, but that's all I'm assuming is that you know how to count and you know how to speak English. So this is not going to be, or rather it's going to quickly become boring for anyone who has, for example, a degree in science of any sort, whether it's chemistry or mathematics or physics, or even if you're generally just well read in these particular subjects. I'm going to be taking you back to, for the rest of you, primary school, or at least early high school. Now, of course, I did teach high school mathematics and science, so I have some understanding of what, the majority of people out there were able to garner from, the 13 years or so they spent in high school. So I've got an idea of what your starting point is. But I also recognize, of course, that very many people who pass through high school just never get these particular lessons I'm going to be delivering today in 2 senses. First, the teachers weren't particularly great and perhaps didn't deliver the material in a particularly interesting way. And second, and more importantly, you as an individual might never have been interested in any of this stuff. And quite right too. Unless you're like me, you won't have found any of this particularly interesting. But, hey, if you can remember some basic number theory and even some chemistry and physics from high school, this could be the podcast for you. It's going to be unusual, absolutely, because this episode ostensibly is about the stratospherically high-level complexities and cutting-edge knowledge that is quantum computation. But here I'll be taking it all the way back to prime numbers and what chemical elements are. Why am I going to be touching on any of that? Well, best we go straight to the book, to the Fabric of Reality to begin with, read a little and take it from there, and things will slowly unfold. I'm going to be taking it very slow because the top of the mountain that we're looking for is Shor's algorithm. And I don't want to leave any of you trekkers behind if you're interested in doing this, interested in trying to understand Shor's algorithm. So we're going to take the most gradual winding road up this mountain as we possibly can, rather than, hauling ourselves vertically up the sheer face, which is what I find so often if I'm trying to learn some new area of physics or something. You try and understand string theory by watching some YouTube videos, and what you get is, well, there's the professor at the top of the mountain that already has reached the pinnacle, and what they're going to do is to ask you to climb the sheer face. In other words, they're assuming so much prerequisite knowledge already. I'm not going to do that. So let's just get into it, okay? David writes on page 214 of the Fabric of Reality here in chapter 9. Quote, "The fact that the repertoire of the universal quantum computer contains environments whose rendering is classically intractable implies that new classes of purely mathematical computations must have become tractable too, for the laws of physics are, as Galileo said, expressed in mathematical language. And rendering an environment is tantamount to evaluating certain mathematical functions, and indeed, many mathematical tasks have now been discovered which could be efficiently performed by quantum computation, where all known classical methods are intractable. The most spectacular of these is the task of factoring large numbers. The method known as Shor's algorithm was discovered in 1994 by Peter Shor of Bell Laboratories. While this book was in proof, further spectacular quantum algorithms have been discovered, including Grover's algorithm for searching long lists very rapidly. End quote. So what we just read there was, quote, that many mathematical tasks have now been discovered which could be efficiently performed by quantum computation, where all known classical methods are intractable. The most spectacular of these is the task of factoring large numbers. The method known as Shor's algorithm was discovered in 1994 by Peter Shor of Bell Laboratories. So, end quote. So, our problem there is about factoring large numbers. Firstly, what does factoring even mean? What is factorizing about? Well, if you've got a number like 12, we can say that the numbers that multiply together to give 12 are its factors. So like 6 and 2, because 6 times 2 gives you 12. So 6 and 2 are some factors of 12. Okay, but that's not quite what we mean in the context of Shor's algorithm and what David's talking about and what we're talking about in general when it comes to factoring. What we're really interested in is prime factorization, the prime factorization of a number. So what prime numbers, when you multiply them together, give you 12? Well, consider that we've just said that, 6 times 2 is 12, but 6 isn't prime. 2 is, but 6 isn't. What does prime mean? Prime means it's a number that has no factors except itself and 1. 2 is the first and the lowest of all the prime numbers. Its factors are 2 and 1. Or, the number 7 is prime because you can't break that down any more simply than 7 times 1 gives you 7. There's no other integers that you can multiply together to give 7. But numbers that aren't prime, like 6 or like 8, for example, they're called composite. Now, sure, with 8, you can have 8 times 1, but you can also have 4 times 2, and as soon as you have something other than just the number times 1, then you've got this composite number. But just for our purposes now, let's just focus on 12. What prime numbers multiply together to give 12? Well, let's take our 6 times 2. Like we've already said, 2 is prime, so we found one of them. 2 is one of the prime factors. As for 6, well, we can break that down. What are its factors? Well, 6 is equal to 2 times 3. Aha! 2 and 3, they're both prime. So then 12 becomes 2 times 6, or 2 times 3 times 2. Or another way to write that would be 2 times 2 times 3. Or in other words, 2 squared times 3. And so we say the prime factorization of 12 is 2 squared times 3. Its prime factors are 2 and 3, which you write as 2 squared times 3. It's all then just prime numbers. Okay, what we've got there, 2 squared times 3, 2 lots of 2 and 1 lot of 3. That's all prime numbers. Hence we call it the prime factors of 12. Okay, so now the remarkable fact about mathematical reality is all whole natural counting numbers can be factored in this way. No matter the number, you can factor them into primes. Isn't that cool? That's really cool. And this fact about reality, about mathematics, it's even got a name. It's so important. It's called the fundamental theorem of arithmetic. And if you want to state it semi-formally, it says every positive integer can be expressed in exactly one way as a product of prime factors. Exactly one way, that is, except for rearranging the numbers. It's also called the unique factorization theorem, but I like fundamental theorem of arithmetic. That sounds much cooler. This makes the prime numbers in mathematics into something like the elements on the periodic table. So as prime numbers are to mathematics, elements are to chemistry. Every positive integer can be decomposed into the product of prime numbers, and everything chemical can be decomposed into elements. Now, if you don't know what I'm talking about there, well, out there in physical reality, anything you can point to that's made of matter, which is to say chemicals, well, all of that stuff, anything you can point your finger at, you go, well, that's made of chemicals. And all matter is made of is chemicals. And all of those chemicals, all of that matter can be broken down into simpler things, unless you've already got an element. So let's say you've got ocean water. Okay. Ocean water, for argument's sake, we can just call it salt water. Okay. In reality, there's quite a few chemicals in ocean water, but presume, for argument's sake, it's just salt water. You've taken out all the other rubbish that might be in there, and all you've got is a mixture of salt and water in your ocean water. But if you wanted to break down that ocean water, that salt water, into its constituent substances, then what you could do is you boil away the water and then you collect it in something called a condenser. That process is called evaporation and condensation, or distillation even. And what you get as a consequence of that, boiling away the water and then condensing it again, is you collect the water and you've got pure water, pure H2O on the one hand, and what you've left behind is pure salt. So you've got two pure substances now. And these two pure substances, the water and the salt, they're known as compounds. They're also called pure substances because no physical means of separation can be used to further break them down. You've got pure water on the one hand and pure salt on the other hand, and they're known as compounds because they're each made up of elements themselves, even simpler things. The water is H2O, that's hydrogen bonded to oxygen, and the salt is sodium chloride, NaCl, sodium bonded to chlorine. Now, although no further amount of distillation or filtering or centrifuging, name your physical process, can separate the hydrogen from the oxygen or the sodium from the chloride, you can use chemical means of separation. So not physical means, but chemical means. Okay, so the chemical means are a kind of physical means, but here we get into the ambiguity of language, and we're distinguishing between purely, or I would say, mechanical physics and chemical bonding, the artificial dividing line between the two subjects, physics and chemistry. So anyways, you can separate hydrogen from oxygen in water. You just need electricity. One can use something called a Hoffman voltameter that looks like this. And if you're watching on YouTube, what you'll see is that one of the terminals is positive and the other one is negative. And long story short, this thing breaks the bond between the hydrogen and the oxygen in water, and you end up with the two gases, hydrogen and oxygen. Now you've got elements. Hydrogen and oxygen appear on the periodic table. Water's not on the periodic table. Pure water's not on the periodic table, but hydrogen and oxygen are. Elements, like hydrogen and oxygen, are more basic than compounds because now, once you've got an element, no matter what you throw at the oxygen or the hydrogen in terms of chemical processes, you can't simplify them any further. There's only one kind of atom that exists in oxygen gas, oxygen atoms. And the same is true of hydrogen. There's only hydrogen atoms in the hydrogen gas. Water, on the other hand, pure, though we say it can be, consists of chemically bonded hydrogen and oxygen to make the water molecule. Now, as for sodium chloride, that's regular table salt, that you get from evaporating the water away from ocean water, well, it's made of the element sodium and the element chlorine. And never a more profound point can be made about the wonders of chemistry than by considering what sodium and chlorine actually are. The sodium is a very reactive metal. It's so reactive that if you just take a small amount and throw it into some water, it catches fire and can sometimes even explode. Go to YouTube and just look up, sodium and water reaction, and you'll see what I mean. It's a remarkable thing, this sodium stuff, because it's a really soft metal. It's a metal, just like many other metals are, but, it's shiny and it's going to conduct electricity, but, you can cut it with a butter knife. It's really soft. And like I say, you throw it into water and it'll catch fire. So it's one of these weird situations where if you have a fire that involves sodium, throwing water on it won't put the fire out. It'll just make things worse. So that's sodium. And then on the other hand, in your table salt, not only do you have sodium, a form of sodium, but you also have chlorine, a deadly poisonous gas. But when you take the sodium, an explosive metal, and chlorine, a deadly poisonous gas, and you chemically bond them together, the deadly gas and the reactive explosive metal come together to make a rather harmless spice that you add to your fish and chips. Salt, sodium chloride, shares very few properties of either the sodium metal or the chlorine gas, the two ingredients, if you like, that make it up. So I know this is a meandering way to explain things. My point here is that you can get down to some fundamentals. You can get down to some basics. There's a base set of substances that make up all the matter in the universe, and they're called the elements. From the elements, from these things on the periodic table, everything else that you can point to out there in the universe is made of this stuff. Okay, so ignore neutron stars and black holes and exotic stuff like that. But let's say everything on the Earth that you can point to, just about, is an arrangement of elements of some sort or other. And yeah, for whatever you can point to, it can in theory be decomposed, as we say, into its constituent elements. That's the technical term in chemistry, decomposition. The decomposition of water results in hydrogen and oxygen. For salt, it's sodium and chlorine, and so on it goes. Now, in a similar way, all of our counting numbers, every number you can think of that's a counting number above, 0, 1, 2, 3, 4, 5, 6, 7, on forever, can be considered a rearrangement of prime numbers. All numbers are either prime numbers themselves, like substances out there in the universe, everything is either an element, or they result from the multiplication of prime numbers. In the case of chemicals, they result from the chemical combination of elements. That's a fun fact, especially if you don't know it already. Figuring out the prime factors of random numbers is a little like, it's a puzzle you can do. Just think of any number that's not ridiculously large. Okay, let's do this as an exercise. This is what I'm going to be doing in this episode. Okay, we're going to be doing a few little mathematical exercises. Let's begin modestly. Let's begin with the number 100. Here's what you do. Just pick any two numbers, any that you like, that when you multiply them together, you get 100. Okay, what's going to jump to mind for most people? Maybe 50 times 2, maybe 10 times 10. Let's go with 10 times 10. Well, 10's not prime, okay, but 10 itself is 2 times 5. Aha. So 2 times 5 is 10. So therefore, if you want 100, you've got 10 times 10, which means 2 times 5 times 2 times 5. Or better yet, 2 times 2 times 5, just rearranging those numbers, which means 2 squared times 5 squared. There's our prime factors. Or our prime number decomposition. And decomposition there is also the correct term, just as it was in chemistry. Now, notice that we chose randomly, right? We said 10 times 10. Now, you might think, but I could have said 25 times 4 or 20 times 5 or 50 times 2. Any of those would have also resulted in 100. Well, you do the exercise. You can prove it to yourself that no matter where you start from, you're going to get a unique prime decomposition. For example, 25 times 4, if you had started there, well, 25 is 5 times 5 and 4 is 2 times 2. So once again, you're left with 25 times 4, 5 times 5 times 2, which is 5 squared times 2 squared, or in other words, 2 squared times 5 squared, which is what we got when starting with 10 times 10. Okay, I'm labouring the point. Where am I going with any of this? And what it's got to do with quantum computers? We're getting there. But as I say, we're taking the long route because, the view is nicer and we're taking a nice stroll in order to get there. Some might like the highway. I like the coastal trek. Lots more sights to see along the way, although it's going to take us a little bit longer. Here's the thing about prime factorization. If you stick with small numbers, like 100, things are pretty easy. But it doesn't take long before you begin to have troubles. It takes much, much longer just by adding another digit. 100's got 3 digits, but, let's do 1200. Now we've got 4 digits. How much harder is it going to be? Well, let's see. Let's see how much longer it takes this time. All right. 1,200 is 120 times 10. Okay. So 120. Well, that's 12 times 10. So we've got 12 times 10 times 10, which we're using the numbers that we've already used previously. So we can say, well, 12, that's 2 squared times 3 times 10 times 10. So we've got 2 squared times 3 times 2 squared times 5 squared, which is 2 to the power of 4 times 3 times 5 squared. Okay, That took a little bit longer. There's a lot more numbers involved there. Okay then, let's take it up a notch. Let's pick a 5-digit number. 14,388. We've got 5 digits and apparently nothing related to what we've seen in the previous examples I've been through with 12 and 100 and 1,200. So what to do? Well, it's an even number, ends in 8, 14,388. So that helps, the fact that it's even. So it must be 2 times something. So we can get out our calculators and divide through by 2, and you end up with 7,194. Okay, we're making progress. 2 times 7,194. Even again. So once again, get our calculator out. We'll have 2 times 2 times 3,597 after dividing by 2 once again. Oh well, 3,597. Ba-bow. Not an even number. Maybe it's divisible by 3 though. Well, there are divisibility tests that I'm not going to go through now, but if you try it out yourself with a calculator, you'll find out that no, it's not divisible by 3. There's a remainder left over. So what's the next prime number? 5. But, well, if you do remember this divisibility test, you will know that all multiples of 5 end in either 0 or 5. Well, okay, let's keep going. We'll try number 7 next. That's the next prime number. That's no good. What about 11? Jackpot. So now we've got 2 times 2 times 11 times 327. That equals 14,388. Well, good. 327 looks quite promising, actually. It's not even, but it looks like it could be a multiple of 3. And indeed, it is. It is. It's 3 times 109. So now we're up to 2 times 2 times 11 times 3 times 109. 109 now. Well, you can check for yourself. You can check for yourself that in fact 109 is itself a prime number. It's got no factors except itself and 1. So only 1 times 109 equals 109. So returning to our original problem, 14,388 has a prime factorization of, reordering the numbers a little bit here, 2 times 2 times 3 times 11 times 109. Or a better way to write it, more compact, is 2 squared times 3 times 11 times 109. Well, that was quite a bit of work, even with a calculator. On the other hand, if I give you a calculator and 2 squared times 3 times 11 times 109, well, you can get that done as quick as it takes to punch the numbers in. Multiplying numbers together to get an answer is easy, relatively speaking. But decomposing that same number into its prime factors takes a lot longer. You just try it. If I pick some random primes, 2 to the power of 3 times 5 times 7, and I say, what do you get on the calculator? It's easy. It'll take you a few seconds. But if I say, okay, find the prime factors of 12,566, well, now all the work is still ahead of you. You don't know what to start, punching into the calculator. Well, it's even, so divide by 2, begin there. And the thing is, even if you give this job to a computer, it faces a similar challenge. The same challenge, in fact. It's much harder to search for the prime factors of some big number than it is to multiply out numbers to get a bigger number. This fundamental fact of reality, that finding factors is hard and exponentially harder for every single digit you add. So 4 digits is exponentially a harder problem than finding the factors of a 3-digit number, and 5-digit numbers are exponentially harder than 4 digits, and so on and so forth. It means the problem becomes intractable in the technical sense that we've talked about in this chapter before. Remember how David Deutsch actually defines intractability earlier on in the book? Well, he wrote back then, let me return to this. This is coming from page 198, and he wrote, quote, "What counts for tractability, according to the standard definitions, is not the actual time taken to multiply a particular pair of numbers, but the fact that the time does not increase too sharply when we apply the same method to ever larger numbers." End quote. And then David goes on to explain that if you increase the number of digits in the numbers you are multiplying, multiplying 2 3-digit numbers to 2 4-digit numbers, the time taken is not vastly different. Indeed, he does a rough and ready calculation back there in the chapter in order for him to make the point that the time taken is around 30% more for each digit that you add. But on the other hand, the reverse of multiplication, factorization, becomes intractable because for each digit that you add, going from 3 digits to 4 digits to 5, 6, whatever, the increase in time taken for each additional digit is not just 30%, it's 300%, a factor of 3 times more, tripling the running time, he says. And David goes on to write, quote, "So the running time would increase in geometrical proportion, that is, exponentially, with the number of digits in the number we are factorizing. Factorizing a number with 25-digit factors by this method would occupy all the computers on Earth for centuries. This is what we mean by saying that the factorization of large numbers is intractable," end quote. Now, this fact about reality, that finding the prime numbers of some number can be very hard and indeed intractably difficult, and once you get to a number that is the product of factors, each of which is 25 digits long, we find it would occupy all the computers on Earth for centuries. That fact can be exploited, and it is exploited by those who want to send secret messages, and that includes you, of course, almost every day, although you might not be aware of it. Every time you want to transmit, for example, information from your credit card or your debit card, or these days, of course, from your mobile phone, to your bank, you want to transmit information about paying for something, you want that information to be secret so that even if someone intercepts it, there would be nothing useful they could do with it. You don't want them to have access to your private passwords and so on and so forth that allow you access to your bank account. We want that information to be hidden somehow. Encrypted is the word we use. The information is scrambled, hidden in a secret code of a kind that only the bank can decode. Well, how can that work? Well, there was a method figured out in 1977, and that's known as the RSA crypto system. RSA stands for Rivest, Shamir, and Adelman. They're the 3 mathematicians, computer scientists actually, and cryptographers, if you want to be precise, all from MIT, the Massachusetts Institute of Technology, and they created the system. A curious part of the history of this is that another fellow, Clifford Cox was his name, a British mathematician working for a British intelligence agency, he had actually discovered the same system 4 years earlier, back in 1973, but no one knew because he worked for the intelligence services, so his work was classified. So he gets remembered only as a footnote to all this, sadly. The RSA system is a kind of public key cryptography, so it's called. Now, in RSA cryptography, RSA numbers can contain, 100, 600 digits, or 1,200 digits in some cases. So numbers that are 600 or 1,200 digits long. Numbers that would take many, many lifetimes of the universe to factor, using all the classical computers on Earth working together. So, intractable. For all practical purposes, impossible to do because the factors are going to be around half that length, a little over 300 digits long for a 600-digit long, number. Examples of these RSA numbers are out there. You can find lists of them on Wikipedia. And cash prizes are offered if you can find the prime factors of them. For all the smaller ones, like that are only like 100 digits long, people have found the prime factors. But those factors are only, 10 or 12 digits long, something like that. Not the 25-digit long factors that David was talking about. The largest one that there's a cash prize for is 617 digits as far as I can find out. And that's more like the size of the number that is used today in the RSA crypto system. So how's this all work? Well, let's do an example. And I'm not going to hide the fact that I'm just stealing this. I'm stealing this example, actually from an Australian mathematician from Deakin University. Her name is Victoria Lynn Batten. So I'm stealing all of her numbers rather than trying to think up them. I've been doing enough of that already, and I'll do some more of that later on as well. So let me use her numbers, and I'll turn it into my own explanation because, like I say, Otherwise, it just takes too long to do all this. So let's begin. So say I'm in the business of trying to transmit to you a secret message. Let's assume you're on the other side of the planet and I need to get to you the secret information about the cost our company that we happen to share is going to be charging for some new widget we've been working on inventing together. Let's call the cost of this new thing that we've invented $99. I want to transmit the number 99 to you without it being feasible for anyone who intercepts the message to possibly know that 99 is encoded in it somewhere. Here's what we do. You start by choosing a couple of prime numbers. Now, in reality, of course, you choose really big ones that are so unwieldy, no computer can possibly figure out what they are once they've been multiplied together. We're going to make this artificially very easy just to see the process. Okay, so we're not going to use the big numbers. So you're going to find this is easy, but in reality, you'd use big numbers. And again, when I say big numbers, I mean hundreds of digits long, which makes the word unwieldy a serious understatement. We want wieldy. So we're going to stick with something small. Okay, so let's say you pick 11 and 17. They're going to be your prime numbers. As we do in these things, we're going to call them P and Q. P equals 11, Q equals 17. Okay, step 2. We're going to multiply P and Q together to get N, okay? P times Q is 11 times 17, that's 187. N equals 187. This N is one of your public keys. It doesn't matter if anyone knows N. In real life, N is absolutely massive, right? Because P and Q are absolutely massive. Now, what we also need, you've got one public key, you've got your N. You also need another one, and this one's going to be a lot smaller. In the business, they call it E. E for exponent, and we'll see why in just a second. The rules for generating E are as follows. Firstly, subtract 1 from P. That gives us 10. Okay, 11 take away 1, 10. And take away 1 from Q to give us 16. Then multiply these two numbers together to get a new number, okay, P minus 1 times Q minus 1, and get 160. Now, find the prime factors of 160. Okay, well, 160 is, we're just going to go through what I've already described to you in the earlier part of this podcast. We go through this process. Okay, 160 is 16 times 10. That's 16 is 4 squared, and 10 is 2 times 5. So figure it all out. You've got 2 to the power of 4 times 2 times 5. So in other words, 2 to the power of 5 times 5. So the prime factors are 2 and 5. Okay, 2 to the power of 5 times 5. Now, because of... I'm doing an explainer video here. I'm not going a formal proof by any stretch of the imagination. So let's just say, because of mathematics, go and look up the details if you want. Here's a link. Okay, here's a link, and hopefully I'll remember to put this in the description to this video, and you can check, okay, for yourself. That the reason is, and we'll sort of touch on this later on, E can't share any factors with 160. So it can't be 2 or 5. It should be prime, but not P or Q either. So let's just pick the number 7. Let's let E equal 7, okay, because it meets all of our criteria. It can't be 2 and 5, and it can't be P and Q. All right. So now we're ready. Now we're ready to say we've got a system of encryption. Given we've got an N and we've got an E, and these are our public keys. You can take N and you can take E and you can publish them wherever you like. There are tools online actually to help with this. Here's one of them. So, just to recap, what are we doing? I'm wanting to transmit to you some top secret business information that our competitors, we just don't want them to know. It's the number 99, that's going to be the price of our new widget. We don't want those pesky competitors knowing the price before release date, because we're going to get lots of publicity by coming in, under $100 before they have a chance to react and change their own price and catch all the social media buzz, whatever. And we know they're watching our conversations. So I need to get this 99 to you secretly. By the way, it doesn't need to be a number. It could be any message at all. We can convert that into a number. After all the keys on a computer keyboard are represented by numbers in the computer system. Our keys on regular keyboards conform to what's known as the ASCII system. Every letter has a number, and every symbol on the keyboard, indeed, has a number associated with it. So in theory, you could have a long string of numbers that can be encrypted using the system I'm about to tell you about, and then decoded using a table like this one. Or, of course, a regular computer will do it quick smart for you. Okay, so what I need to do is to take this 99, which no one knows, and also take my N and E. And N and E we both have access to, and everyone has access to. That doesn't matter. And I raise my secret information, my secret number, 99, to the power of E. So 99 to the power of 7. Well, that's an even bigger number. In fact, it's 93,206,534,790,699. Well, now we take that number and divide it by the N we found earlier, 187, and my calculator tells me it's 498,430,669,329.94167470588235, and so it goes. The reason for this will become apparent after a quick diversion into modular arithmetic. Okay, so let's try and keep that in mind. What's modular arithmetic now? Well, basically it's counting in a circle. Everyone's familiar with it. You do it with an analog clock. Well, at least anyone who's able to read an analog clock. With a regular analog clock, we count in lots of 12. The purpose of modular arithmetic, among other things, is to enable us to talk about remainders. And it's sometimes to find how a sequence of numbers, in some sequence of numbers, the remainder, when you're dividing by some constant, is periodic. The remainder is periodic, or can show periodicity. That is to say, it repeats over time. This is going to become absolutely key for decoding all of this stuff. All right, let's talk about modular arithmetic. All right, let's get into this. Consider our clock. If it's 9 a.m. now, we've got a very basic clock, with no minute hand, which just tells us what hour we're in, then the hour hand just points to 9, basic. What's it going to be pointing to 5 hours from now? Well, if it's 9 a.m. now, it's going to be pointing to 2 p.m. later on, so it's going to be pointing to 2. Okay, so modular arithmetic, 9 plus 5 does not equal 14, because there is no 14 on the clock. In our system, we've only got numbers up to 12, so instead, 9 plus 5 gives us 2. That's just how this works. What we say is that 2 is the remainder from 14 given a modulus of 12, or 14 equals 2 modular 12, or 2 mod 12. Or more formally, you usually see it written this way: 14 equals 2 mod 12. I think of it as 14 is 2 mod 12. And modulus, this is a word that's used in English rather often as well. In fact, I kind of overuse it at times. It's sort of fancy English. It means, the word modulo means ignoring a special case. Like, I might say something like, the free market is the absolute best way for people to create new stuff in the fastest way possible. Modulo crime that you get from time to time. You get crime under every system, free or not. So we can ignore that, okay? It's modulo the crime. So the free market is the fastest way for us to create new things, ignoring the crime. Modulo the crime. I'm admitting, okay, when I talk about the free market, that there's bad stuff that goes on. But there's always bad stuff, whether you've got a free market or not. So no matter what, we can put to one side the bad stuff that exists everywhere. Modulo that. Ignoring that. Or falsification is how we find the best explanations in science. Modulo the Duhem-Quine thesis results. Namely, ignoring the idea that experiments sometimes fail. Okay, belaboring the point. 14 is 2 modulo 12, or modular 12. Or in mathematics, it's usually just said as mod. 14 equals 2 mod 12. Let's do another example, because this will come up again, and we're keeping in view this idea of wanting to understand Shor's algorithm from the ground up. Let's not use 12. Let's think of another number like 5. So we're going to imagine a clock now that just goes from 1 to 5. Let's pick a random number. 42. 42, the meaning of life, according to Douglas Hofstadter. 42 equals something mod 5. Well, what? Well, 42 equals 2 mod 5. Why 2? Because 2 is the remainder you get once you divide 42 by 5. 5 goes into 42 8 times with 2 remaining. The 8 appears nowhere in our equation there. It's implicit. It's not explicit. You can do this yourself now. What's 37 given a modulus of 5? 37 equals what mod 5? How many times does 5 go into 37? Well, it goes in 7 times. How many are left over? 2. In other words, if you had a clock that just goes from 1 to 5 and you're counting round and round up to 37, your hand is going to point to the 2 hand once you get to 37. Okay, because once you get to 35, it's going to be back to 5 again, start all over again. So you go 5, 10, 15. Okay, round to 35, then 2 more. That's why. But what if it ends up on 5? What's 5 mod 5? 0. Okay, so 5 equals 0 mod 5. It's just the same. Once we get to 6, then we're back to 1 again. So 6 is 1 mod 5. That's important to know. Okay, it's important to this idea of when the modulus is 1 is going to come up again. So 6 is the first time you have a remainder of 1. 11 is the next time you've got a remainder of 1. 16 is the next time you've got a remainder of 1. Then 21, then 26. Notice we've got a pattern there. Already we can see periodicity in the case of the multiples of 5. 5, 10, 15, 20, 25, 30. Okay, the numbers 11, 16, 21, 26 all have a remainder of 1. And those numbers, 11, 16, 21, 26, notice the final digit there, 1, 6, 1, 6. That's got a period of 2. It's repeating every 2, right? It's repeating every 2 numbers it's repeating. We're going to come back to that. So let's remember, to recap, our problem here is going to be to decrypt a message that consists of a vastly huge number. Hundreds, 600, or maybe even thousands, 1,000 or 1,200 or more digits long. And that number is itself a product of huge prime factors. The only way to decrypt such a message hidden in this number is to find those prime factors. And the only way we know how to do this so far, that I've explained to you so far, is to begin at 2 and then start checking one at a time. Okay, you've got this big number and then you check. Does 2 go into it? No. What about 3? No. 5? No. 7? No. Just keep going one after another and searching the space of all prime numbers until you finally get one that divides into it evenly. But the problem is, when you've got these huge numbers that are hundreds of digits long, there are just so many of them, so many prime numbers to check, that this process would take a regular computer, indeed, as David says, all the regular computers on all the earth working as fast as possible. It would take literally trillions of years to do. That's how many prime numbers there are and how hard it would be to search that space because we're talking such big prime numbers. There's got to be a better way than just sequentially searching one after another, beginning with 2, right? Well, yes, and that's what we're going to talk about next. So here's 2 famous formulae, named for Leonhard Euler, a Swiss mathematician born in 1707 and renowned as one of the greatest math geniuses of all time. That second formula there, typically known as Euler's identity, includes E, okay, the exponential for the number, defined in part by the fact that if you draw a curve, a graph of y equals e to the x, well, e is this special number. It's about 2.7 something or other, such that y equals e to the x has a value for its derivative of every point x, which is equal to y. In other words, if you differentiate y equals e to the x, then you get e to the x. If that makes no sense to you, never mind. You can skip that. It's calculus, okay? We're not going to do a calculus lesson here. If you want an introduction to calculus, let's see my video here. But also there you have related in one formula that number e, crucial in calculus, and we also have I, the so-called imaginary number, the square root of -1, the basis of the complex numbers. So we've got pi there as well, and we've got 1, and we've got 0. Okay, all of these foundational numbers there in one equation, one amazing identity. Okay, so Euler gave us that identity and the other one there, which is, well, I'll come to that. He was fascinated by this idea of repeating patterns in primes. Let's just recap. 42 equals 2 mod 5, because in the general case, if you write down something like a equals x mod n, that means that when you divide a by n, you get a remainder of x. A over n gives you a remainder of x. Now, Euler figured out a lot of this stuff. Right? He was obsessed, the good kind of obsession, he was passionately curious about numbers and arithmetic and counting and prime numbers in particular. He was noticing and explaining patterns where no one else had before, and he saw links between exponentials and periodicity. Hence his formula here. If you know anything about trigonometry, you'll know it's about periodicity. Patterns repeating, okay? It's waveforms, you know, you have the sine wave and the cosine wave, and so you can figure out the period of things, which is how often something repeats itself. In terms of patterns of numbers, for example, you know, consider the powers of 3, okay? 3 to the power of n, okay? N's the integers, 1, 2, 3, 4, 5. So you get 3, 9, 27, 81, 243, 729, 2,187, 6,561. These are the powers of 3. Now, consider each of those, okay, the powers of 3, in terms of mod 10. Okay, mod 10. So we're going to be dividing them by 10. So 3 equals what mod 10? 9 equals what mod 10? 27 equals what mod 10? Okay, I'll write that down here. Well, it's what the remainder is, okay? So 10 goes into 3 0 times. It doesn't go into 3 at all. So you're left with just 3. 10 goes into 9 0 times. You're just left with 9. But 10 goes into 27 twice with 7 left over. 10 goes into 81 8 times with 1 left over. So we're just writing down the remainder, okay, each time. How many times does 10 go into 243? 24 times with 3 remainder. How many times does 10 go into 729? 72 times with 9 remainder. These are the powers of 3. So we've got a sequence now of remainders. 3, 9, 7, 1, 3, 9, 7, 1. It's repeating itself. In other words, those remainders, when you're dividing by 10, give you a pattern, periodicity. 3, 9, 7, 1. The period is 4, we say. It repeats every 4 digits. And also, notice that the 1's there, okay? 1 is very important, as I said earlier, and it's come up here again now. There's a remainder of 1. Let's just do another example, just for the fun of it. Powers of 2, okay? Everyone likes powers of 2. 2, 4, 8, 16, 32, 64, 128, 256. Well, let's do mod 7, okay? So we're going to be dividing each of these numbers by 7. How many times does 7 go into 2? It doesn't go into 2 at all. It just leaves the 2 on its own. How many times does 7 go into 4? Again, it doesn't go in. It leaves 4 on its own. How many times does 7 go into 8? Now, finally, it goes in once with 1 left over. How many times does 7 go into 16? Twice with 2 left over. How many times does 7 go into 32? Well, it goes 4 times. 7 4s are 28, with 4 left over to take us up to 32. Well, can you see the pattern already? The remainders are 2, 4, 1. Then 2, 4, 1, 2, 4, 1. We've got a pattern of 2, 4, 1. Then it repeats a period of 3, just 3 digits, and it ends in 1. Isn't that remarkable? And it was Euler that figured this stuff out. So that's absolutely amazing. Surprising. Should be surprising to you. I find it just really cool. So we've always got this situation where in modular arithmetic, if we're finding remainders of things, they have a period of some length And that period always ends with 1. We know where it ends because it's going to end where we find the number that's got a remainder of 1. Now, there are proofs for all this. I'm not proving anything to you. That's way too hard. I'm asking you to take it on faith that this, in fact, is what's going to happen. You can look up the proof if you like. So the thing is, if you have a number x and a number n, and they're relatively prime, so we call it, that means that they share no factors. Then this very property of having a periodic sequence like this, always ending in 1, holds all the time for this form of expression. You know, x mod n, and then x squared mod n, and x cubed mod n. So for 3 mod 10, the period is 4 numbers long, okay, for your powers of 3. And the period of 2 mod 7, the powers of 2, the period is 3, okay, 2, 4, 1. Now we call the period R, letter R. And this is going to be absolutely crucial. One of the whole points of Shor's algorithm is going to be to find R, the period, how frequently this modulus reappears, the remainder reappears. R is the smallest number such that x to the power of R equals 1 mod n, where the 1 is the remainder that you get, and R is the period. Namely, in our examples with powers of 3, 3, 9, 27, 81, the powers of 3, the period happens to be 4. In other words, 3 to the power of 4 is when you first get a remainder of 1. 3 to the power of 4 equals 1 mod 10 in our earlier example. But 3 squared is 9 mod 10. And well, just look at the others. Okay, they don't give you the 1. So knowing R, the exponent for when the remainder first becomes 1, gives us the period. All right, now if you get all that, you're really making progress. You're really making progress. Give yourself a pat on the back. We're getting to Shor's algorithm. We're getting to parts of it. You're getting a glimpse into what's about to happen, okay, the big quantum computing stuff. Let's go back to our factoring of large numbers again. And we're going to bring up a different mathematician this time, also an E mathematician, Euclid. So not Euler, but Euclid this time. What Euclid figured out was that rather than starting at 2 and seeing if that divides into our big number, and then 3 and then 5, and sequentially going through all the prime numbers up until you eventually find P by a process of just brute force, so to speak, we're instead going to guess, basically randomly, any old number, okay, because we're going to find the factors of n. We're going to find P and Q. We're going to pick any old number smaller than n. Recall that A equals x mod n. We want to know if A and n are relatively prime. Do they share factors? That's a question of what their greatest common divisor is. Greatest common divisor is a term that's used in proper professional mathematics. But in high school, when I taught this stuff in Australia anyway, we used HCF, highest common factor. An algorithm to find the highest common factor or the greatest common divisor. If people are learning this for the first time, if you're just using small numbers, is to just write out all the factors and to just look in the list of all the factors and to see which ones are the highest. Let's say you've got like 180. Okay, so you want to find this. What is the greatest common divisor of 180? What is common to both of them and the biggest one? Well, literally just list all of the factors of 80 and 100. Well, 80, the factors are 1, 2, 4, 8, 20, 40, and 80. These are the numbers that divide into 80 without leaving a remainder. And 100, it's 1, 2, 4, 5, 10, 20, 25, 50, and 100. Okay, well, 1's in both lists, 2's in both lists, 4's in both lists, but I'm not interested in that. I'm interested in which number is the biggest that is in both lists. That's 20. 20 is the highest common factor or greatest common divisor, whatever you want to call it. But when you've got two huge numbers, it's got to be a better way. So enter Euclid at this point. Euclid was around, some hundreds of years BC, the guy to whom we owe Euclidean geometry. So he was a mathematician of outstanding genius from much earlier than Euler. And this method rarely gets taught in schools. You know, I would only bring it up if someone was, you know, super interested in this stuff. Rarely happened to be the case. It wasn't a part of the standard curriculum. But, you know, people who express curiosity about this stuff, you know, they'd find this fascinating. There was a better way. There is a better way than just writing out the long list of factors. So that's what we're going to do. We're going to see what this algorithm is, this Euclidean algorithm for finding the factors. Now, I should say this version of the Euclidean algorithm, it's blending some more modern ways of doing things. So this is not exactly the way Euclid would do it, but I'm mentioning Euclid because he deserves some credit for this. And in reality, of course, we're using, you know, these huge numbers. N is going to be a huge number. P and Q are going to be huge numbers. We want to find P. So we're going to guess. Okay, we're going to guess. We're going to figure out a guess for what P and Q are. We're going to call that guess A. We're going to use the letter A. If the numbers are relatively prime, then what that means is their greatest common divisor is 1, which means they don't share any factors at all. I know I'm repeating myself, but remember, we're doing this if you're curious about this stuff, but you don't know much of this mathematics. So let's do a silly example, an easy example. Let's say N is 35. And if you knew nothing about, you know, what are the factors of N, well, you might, let's guess something. Let's guess 8. I know that's silly to guess 8, but this is illustrative, okay? Because if you've got a huge number, you just don't know what to guess, and so you're going to guess wrong. Invariably, you're going to guess wrong. Now, 8, for our purposes, it's clearly a bad guess on the one hand, because you know it's not going to work, but it's a good guess on the other, because straight away it is co-prime with 35, which is what we're after. It shares no factors with 35. The factors of 8 are 1, 2, 4, and 8. And none of those are factors of 35. Now, we're going to need a calculator because we want to know the powers of 8. Okay, the powers of 8 are 8 to the power of 1 is 8, 8 squared is 64, 8 cubed is 512, 8 to the power of 4 is 4096. Now, mod 35, which is the number that we're interested in, mod 35 of each of those numbers is 8. Remember from earlier on, you know, how many times does 35 go into 8? 0 times, leaving you with 8. How many times does 35 go into 64? It goes 1 with a remainder of 29. How many times does 35 go into 512? Use a calculator, but you find out that it leaves a remainder of 22. And 4096, we actually hit 1 because 4096 mod 35, well, it's 35 times 117 gives you 4095. Okay, check with a calculator yourself. So that means 35 goes into 4096 117 times with a remainder of 1. And that's what we're after. It takes some calculating, but you can get there. You know, you do it with guess and check. Now, for us to use Shor's algorithm, to use Euler's method here, R must be even. All I can say in the explanation for why it must be even is to trust me for now, we're going to get there. Or you can watch another video that goes into more depth on this. But our formula is going to call for, you'll see in a moment, R over 2. Hence the need for an even R. Okay, R has to be an even value, which we've got in this particular case. Our R is 4. Why is it 4? Because, well, the remainders are 8, 29, 22, and 1. Then it's going to repeat 8, 29, 22, and 1. Once you've found a remainder of 1, that's it. You've found your R. You've found your period. But if R, in our case, wasn't an even number, if it wasn't 4, if instead it was 5, we'd need to start again. We'd need to start again with a new guess for A until we get an even R. Yeah, it can be difficult. So the formula we're about to employ when, you know, we're doing this is that we want to have a condition where A to the power of R over 2 plus 1 does not equal 0 mod n. You don't want a remainder. Now, in order to get the right R, you don't have to search for too long. to find an even r because half the numbers in the universe are even. So you've got a 50-50 chance of picking a good a. So let's go back to, again, one of the key formula, one of the key identities. A to the power of r equals 1 mod n. Now, because it's modular arithmetic, I can actually write, I won't go into the details, a to the power of r minus 1 equals 0 mod n. If you assert that something is 0 mod n, you're saying there's no remainder, zero remainder. In other words, it's a multiple of n. So there must be some other number k such that what's on the left-hand side there, a to the power of r minus 1 equals kn. And again, r has to be even. So let me give you some explanation why, and we're going to have to do some algebra here, and I apologize, but we're going to employ something called the difference of two squares, if you cast your mind back to high school algebra. Namely, x squared minus y squared can be written as x minus y, x plus y, like this. And if you don't know why, don't worry, just take it on faith or go look up the difference of two squares in algebra. Its relevance here is that if we require a to the power of r minus 1 to equal kn, then, bear with me, a to the power of r over 2 minus 1, all multiplied by a to the power of r over 2 plus 1 is equal to kn. Now, how does that work? Well, when you expand the whole thing out, a to the power of r over 2 multiplied by a to the power of r over 2 equals a to the power of r. Okay, this is high school algebra. You just add your indices together. And that's a difference of two squares, and 1 is 1 squared. One more thing. N equals P multiplied by Q. Remember that? They're the original primes we're after all. We want to know P and Q. So N in that formula that we've just talked about, the Kn, can be written as KPQ. So in other words, we've got this now. A to the power of r over 2 minus 1, all multiplied by a to the power of r over 2 plus 1 is equal to KPQ. If you're all at sea right now and you're throwing your hands up in the air and you're completely lost, but you don't want to be, well, pause here, if you like, and prove it to yourself that that formula actually follows. Expand out those brackets and convince yourself. But if you haven't got the algebra, bear with me just for a little longer. We're going to get there. We're going to throw some real numbers in here now. The actual numbers we were using before with 35. Now, what we did then was we guessed that A equals 8. And remember, we found a period of R equals 4. So using the condition that we require, namely A to the power of R equals 1 mod n, that becomes, in our particular circumstance, 8, our guess was 8, to the power of 4, our period is 4, 8 to the power of 4 equals 1 mod 35. Or, to substitute it into our key formula, we can call this our key formula, a to the power of r over 2 minus 1, a to the power of r over 2 plus 1 equals kpq. Substituting all that in, using that, this is what we require, this is what we need to know, okay? This 8 to the power of 4 equals 1 mod 35. Or in other words, as we just said, modular arithmetic allows us to say 8 to the power of 4 minus 1 equals 0 mod 35. And the argument that we used earlier on was 0 mod 35 means that you've got something that divides by 35 exactly. In other words, 8 to the power of 4 minus 1 equals k, some integer, times 35. Now, at this point, we could solve for k, but we don't need to. We want to put it in the form that we had earlier into our key equation. Our key equation is a to the power of r over 2 minus 1, all multiplied by a to the power of r over 2 plus 1, and that equals kpq. In our particular circumstance, substituting in what we know, given a equals 8 and r equals 4, then we can write this down. 8 squared, take away 1, all multiplied by 8 squared plus 1 equals kpq. P and Q, remember, as the Holy Grail, that's what we're after in order to do our decryption. So the highest common factor, or the greatest common divisor of a to the power of r over 2 minus 1 and n is p, while the greatest common divisor of a to the power of r over 2 plus 1 and n is q. This is because in this original formula here, okay, p must divide neatly into either a to the power of r over 2 minus 1, or it's going to divide into a to the power of r over 2 plus 1. One of those is going to be p and one of those is going to be q. Now, if you don't get all of that, perhaps watch this video on YouTube that goes through all of this in more detail. Or actually, if you do pause what I've said above and watch it again, there is enough information there to enable you to prove it to yourself. But I understand if you've never heard this sort of stuff before, it can get a bit tricky. Just keep in mind that we did place a condition about some numbers being co-prime earlier on. That was important. Okay, so let's substitute. Okay, we've got p equals the greatest common divisor of a to the power of r over 2 minus 1 and n, where our n in this example is 35, and a to the power of r over 2 minus 1 becomes 8 to the power of 4 over 2 minus 1, which is 8 squared minus 1, which is 63. And so now we've collapsed all of this down into finding the greatest common divisor of 35 and 63, which is 7. 7 is the number that is biggest that will go into both of those. And by the same argument, q is the greatest common divisor of 65 and 35, which is 5. So that's it. That's what you do. That's how you crack RSA security, right? What's the problem? Well, the problem is that finding r in the first place for a huge number, a really big number, that's the stumbling block. That takes our metaphorical forever because you need to write out all of those powers. It's an intractable problem. But this method is progress because we've gone from a problem where we need to search sequentially all the prime numbers, 2, 3, 5, 7, 9, all the way up to p and q, which is a rather hopeless prospect, to a somewhat less hopeless prospect, finding the period r, which is kind of easier. It's certainly easier for a quantum computer to do. A quantum computer doesn't have to search through all of the primes. It can just find this period. But this is part of the key part of Shor's algorithm in a nutshell, sort of. But we haven't yet introduced anything quantum to do with this, which makes finding the r easy. So let's go there. We need the quantum because if n is really big, and it is, as I keep saying, in RSA, then r, the period of the remainder, the modulus, is going to be almost as big as n. That's a problem classically, because classically you may as well search, all the prime numbers, 2, 3, 5, 7, etc., to find the prime factors of p and q. You may as well do that as find r, being the period of a mod n, where a is your guess. With quantum computing, what you can do is have the quantum computer in a superposition of n states, and you can check. You can check a to the power of 1 mod n, a squared mod n, a to the power of 3 mod n, and so on, up to whatever a to the power of x mod n, until we find a to the power of x is 1. Okay, we get that 1 remainder. Remember, that's our condition that tells us r, when that remainder is 1. But we're not checking sequentially. And if you've got this quantum computer, you can't check sequentially, basically, because, well, you're in a particular universe. And when you look at a computer, when you ask the computer for a result, you're only going to get one result. You're going to be told by the computer that either 3 is a factor or not. It's not much more help than what a classical computer would be. You're kind of randomly selecting to know whether or not a particular number is a factor of n. You'll get, for example, a cubed mod n, which in all likelihood won't be the one you're after. You want the one where you're getting the remainder of 1. But, and here's the key, here's the quantum key to all this. R, the period, is a global property of all the states of all the computers, of the quantum computer, of all the instances of the computer in the various universes in the multiverse. Shor didn't put it quite that way, but this is the insight. Across the multiverse, we would say the period of the wave function, waves have periods, right? That's a thing we can know from within any one universe. It doesn't depend on which universe you're in, because the wave function is a property of the multiverse. It's common to all states, and so therefore, so too is the period. Isn't that cool? Okay, so here's where I'm completely glossing over further details, because then we do need to get into university level physics. We need something called the quantum Fourier transform. What it does is it amplifies the correct state out of all those a to the power of x mod n possibilities. This happens. How does this happen? It happens by constructive interference. All the incorrect answers destructively interfere. And so this way, the correct answer kind of bubbles to the top, so to speak. It is the one that the quantum computer can tell you has the highest amplitude. And the square of the amplitude is the probability, okay, the expectation value, whatever. Now, okay, I fear I'm losing the audience. And if I go into any further detail on this stuff, I'm going to lose everyone. But if you've come this far and you're not lost, then I see my role as having succeeded. I've given you the cab ride to the airport, I hope. And if you want to go further and really want to zoom off into the details of Shor's algorithm, then, well, you can't go past the great Arthur Eckhart, student, protege, we might say, of the great David Deutsch himself. Arthur's like the Obi-Wan Kenobi to David's Yoda. I mean, now, Arthur himself is such a Jedi master himself. He mentors and inspires. He has mentored and inspired countless numbers of quantum physicists over the years. So if you want to learn from a true Jedi master about this stuff, and not some pretender like me, then go to Arthur's video right here, which is where, I admit, I'm distilling out a lot of the high-level technical stuff into this here, very bird's-eye view explanation of things for people with almost no mathematical background. In other words, I've just been stealing his material and bringing it down quite a few notches. And by the way, if you want the history of all of this Shor's algorithm stuff with some quite technical details, Peter Shor himself has a half-hour video here on YouTube, worth looking up. Links in the description. But let's now, that I've given you all that, go back to the book, The Fabric of Reality, and conclude our reading. And I'm going to start at a point where you're going to get a little bit of a giggle, because David writes, quote, Shor's algorithm is extraordinarily simple. That's the funny part after everything I've just said there. Let me go on. David says, Shor's algorithm is extraordinarily simple and requires far more modest hardware than would be needed for a universal quantum computer. Okay. No, but really, as far as the high-level physics and mathematics goes, it is simple. I've been, laboriously starting literally from the ground up, basically primary school level mathematics, to bring you to a point where you can at least glimpse the graduate level physics that follows. That was my task. I hope I've succeeded at that. So if you have some undergrad physics and mathematics level of understanding, then it is simple. And it's also simple in the sense of what it's doing. Simple in David Deutsch's way of explaining what simple is, which is relative to your theory of computation. Finding the period, finding that R, is a simple physical computation. Simple for a quantum computer, not simple for a classical computer. Let's keep going, because now David's going to put an Everettian multiversal spin on everything that I've just been talking about. He goes on, quote, It is likely, therefore, that a quantum factorization engine will be built long before the full range of quantum computations is technologically feasible. This is a prospect of great significance for cryptography, the science of securely communicating and authenticating information. Realistic communication networks may be global and have large, constantly changing sets of participants with unpredictable patterns of communication. It is impractical to require every pair of participants, physically and in advance, to exchange secret cryptographic keys that would allow them to later communicate without fear of eavesdroppers. Public key cryptography is any method of sending secret information where the sender and the recipient do not already share any secret information. The most secure known method of public key cryptography depends on the intractability of the problem of factorizing large numbers. This method is known as the RSA crypto system, named after Ronald Rivest, Adi Shamir, and Leonard Adleman, who first proposed it in 1978. I thought it was 1977. Anyway, keep going. It depends on a mathematical procedure whereby a message can be encoded using a large, say 250-digit number as a key. End quote. So, since the book was written, things have changed slightly and people are using up to 600 digits. In fact, double that, as I've said. I've seen 1200 as another number that's quoted for this stuff. He goes on to say, quote, "The recipient can freely make this key public because any message encoded with it can only be decoded given a knowledge of the factors of that number. Thus, I can choose two 125-digit prime numbers and keep them secret but multiply them together and make their 250-digit product public. Anyone can send me a message using that number as the key, but only I can read the messages because only I know the secret factors. As I have said, there is no practical prospect of factorizing 250-digit numbers by classical means, but a quantum factorization engine running Shor's algorithm could do it using only a few thousand arithmetic operations, which might well take only a matter of minutes. So anyone with access to such a machine would easily be able to read any intercepted message that had been encrypted using the RSA crypto system. It would do the cryptographers no good to choose larger numbers as keys because the resources required by Shor's algorithm increase only slowly with the size of the number being factorized. In the quantum theory of computation, factorization is a very tractable task. It is thought that in the presence of a given level of decoherence, there would again be a practical limit on the size of the number that could be factorized, but there is no known lower limit on the rate of decoherence that can be technologically achieved. So we must conclude that one day in the future, at a time that cannot now be predicted, the RSA crypto system with any given length of key may become insecure. In a certain sense, that makes it insecure even today. For anyone or any organization that records an RSA encrypted message today and waits until they can buy a quantum factorization engine with low enough decoherence will be able to decode the message. That may not happen for centuries, or it may only be decades, perhaps less, who can tell. But the likelihood that it will be rather a long time is all that now remains of the former complete security of the RSA system. When a quantum factorization engine is factoring a 250-digit number, the number of interfering universes will be of the order of 10 to the power of 500. This staggeringly large number is the reason why Shor's algorithm makes factorization tractable. I said that the algorithm requires only a few thousand arithmetic operations. I meant, of course, a few thousand operations in each universe that contributes to the answer. All those computations are performed in parallel in different universes and share their results through interference. You may be wondering how we can persuade our counterparts in 10 to the power of 500 odd universes to start working on our factorization task. Will they not have their own agendas for the use of their computers? No, and no persuasion is necessary. Shor's algorithm operates initially only on a set of universes that are identical to one another, and then it causes them to become differentiated only within the confines of the factorization engine. Pausing there, my reflection. Yeah, this is a key point to notice, and it's something that David Wallace is at pains to make explicit in The Emergent Multiverse, where he talks about, and in his own public lectures on this, the definition of a universe is a slippery kind of a thing when we're talking the Everettian multiverse. A universe can be all the stars and galaxies and as big as that, what we normally call universe, but it can also be something that is effectively isolated from the rest of physical reality that we can observe inside of a box somewhere, namely inside of a quantum computer, or as David is referring to it there, a quantum factorization engine. He goes on to say, quote, "So we who specified the number to be factorized and who wait while the answer is computed are identical in all the interfering universes. There are no doubt many other universes in which we program different numbers or never built the factorization engine at all, but those universes differ from ours in too many variables, or more precisely, in variables that are not made to interact in the right way by the programming of Shor's algorithm, and so do not interfere with our universe. The argument of chapter 2, that was shadows, applied to any interference phenomenon, destroys the classical idea that there is only one universe. Logically, the possibility of complex quantum computation adds nothing to a case that is already unanswerable, but it does add psychological impact. With Shor's algorithm, the argument has been writ very large. To those who still cling to a single universe worldview, I issue this challenge. Explain how Shor's algorithm works. I do not merely mean predict that it will work, which is merely a matter of solving a few uncontroversial equations. I mean, provide an explanation. When Shor's algorithm has factorized a number using 10 to the power of 500 or so times the computational resources that can be seen to be present, where was the number factorized? There are only about 10 to the power of 80 atoms in the entire visible universe, an utterly minuscule number compared with 10 to the power of 500. So if the visible universe were the extent of physical reality would not even remotely contain the resources required to factorize such a large number. Who did factorize it then? How and where was the computation performed? Okay, I'm going to skip a bit. Now, this idea that quantum computers will destroy cryptography, the RSA system, doesn't mean that cryptography itself is a doomed enterprise, because you can have quantum cryptography. David goes on to talk about exactly this, so let's just read through that. We're coming swiftly to the end of the chapter. David writes, quote, I have been discussing traditional types of mathematical tasks that quantum computers would be able to perform more quickly than existing machines, but there is an additional class of new tasks open to quantum computers that no classical computer could perform at all. By a strange coincidence, one of the first of these tasks to be discovered also concerns public key cryptography. This time it is not a matter of breaking an existing system, but of implementing a new, absolutely secure system of quantum cryptography. In 1989 at IBM Research, Yorktown Heights, New York, in the office of the theoretician Charles Bennett, the first working quantum computer was built. It was a special purpose quantum computer consisting of a pair of quantum cryptographic devices designed by Bennett and Gilles Brassard of the University of Montreal. It became the first machine ever to perform non-trivial computations that no Turing machine could perform. In Bennett and Brassard's quantum crypto system, messages are encoded in the states of individual photons emitted by a laser. Although many photons are needed to transmit a message, 1 photon per bit, plus many more photons wasted in various inefficiencies, the machines can be built with existing technology because they need to perform their quantum computations on only 1 photon at a time. The system's security is based not on intractability, either classical or quantum, but directly on the properties of quantum interference. That is what gives it its classically unobtainable absolute security. No amount of future computation by any sort of computer, whether for millions or trillions of years, would be of any help to an eavesdropper on quantum encrypted messages. For if one communicates through a medium exhibiting interference, one can detect eavesdroppers. According to classical physics, there is nothing that can prevent an eavesdropper who has physical access to a communication medium, such as a telephone line, from installing a passive listening device. But as I have explained, if one makes any measurement on a quantum system, one alters its subsequent interference properties. The communication protocol relies on this effect. The communicating parties effectively set up repeated interference experiments, coordinating them over a public communication channel. Only if the interference passes the test for there having been no eavesdropper do they pass on to the next stage of the protocol, which is to use some of the transmitted information as a cryptographic key. At worst, a persistent eavesdropper might prevent any communication from taking place at all, though of course that is more easily achieved just by cutting the telephone line. But as for reading a message, only the intended recipient can do that, and the guarantee of that is provided by the laws of physics. Because quantum cryptography depends upon manipulating individual photons, it suffers from a major limitation. Each photon that is successfully received carrying 1 bit of the message must somehow have been transmitted intact from the transmitter to the receiver, but every method of transmission involves losses, and if these are too heavy, the message will never arrive. Setting up relay stations, which is the remedy for this problem in existing communication systems, would compromise the security because an eavesdropper could, without being detected, monitor what's going on inside the relay station. The best existing quantum cryptographic systems use fibre optic cables and have a range of about 10 kilometres. This would suffice to provide, say, the financial district of a city with absolutely secure internal communications. Marketable systems may not be far away, but to solve the problem of public key cryptography in general, say for global communications, further advances in quantum cryptography are required. Experimental and theoretical research in the field of quantum computation is accelerating worldwide. Ever more promising new technologies for realising quantum computers are being proposed, and new types of quantum computation with various advantages over classical computation are continually being discovered and analysed. I find all these developments very exciting, and I believe that some of them will bear technological fruit. But as far as this book is concerned, that's a side issue. From a fundamental standpoint, it does not matter how useful quantum computation turns out to be, nor does it matter whether we build the first universal quantum computer next week, or centuries from now, or never. The quantum theory of computation must, in any case, be an integral part of the worldview of anyone who seeks a fundamental understanding of reality. What quantum computers tell us about connections between the laws of physics, universality, and apparently unrelated strands of explanation of the fabric of reality, we can discover and are already discovering by studying them theoretically. End quote. End of the chapter. Well, that was an epic episode, I think. I hope I didn't bore too many people with my long diversion in there to the details of some of the underlying arithmetic required for Shor's algorithm. I hope it was informative. But as I say, this chapter could have been a book all on its own. Next time, we're going to go to one of my favourite chapters, the nature of mathematics, which we've talked about all the way back in the beginning of Infinity series on the reality of abstractions. This had perhaps the second greatest impact upon me decades ago when I first read the book, second only to Shadows, which revealed to me the nature of quantum theory and how to understand it via the multiverse. Well, this, the nature of mathematics, made me completely rethink what I'd always been taught and thought I understood about what mathematics is. Many of you will already be familiar, if you're a fan of Topcast, the mathematician's misconception, which I've talked about a lot. But we're going to go back to where it all began, Chapter 10, the nature of mathematics, next time. But until then, I hope that you feel you're informed now about quantum computation and excited about the possibilities and have an understanding of how an understanding of quantum computation is required for an understanding of our deepest theories of the fabric of reality. But until next time, bye-bye.